Okay, so today we're going to keep talking about CSPs. So we'll do a quick recap of what CSPs are, just so we're on the same page. And mostly we're going to talk about how to efficiently solve them. We already saw a bunch of good ideas for quickly solving CSPs last time, and we're going to get the rest of those ideas today. And then we're going to move on into the idea of local search, which is actually very applicable for CSPs, but is an idea for search more generally. So let's remember what CSPs are. They are, at some level, a search problem, but they have their own very specific structure that allows us to use special purpose algorithms beyond the generic search algorithms. So what's in a CSP? There are variables, there are domains which hold the values that those variables can take on, and then there are constraints that say which assignments to the variables are legal. And what you're searching for is an assignment that is complete, that is, it assigns all of the variables and obeys all of the constraints. So, it seems pretty clear what an assignment is. It's a variable, it's like a map, a variable and a value. But what's a constraint look like? And we saw that there's actually two ways to have constraints written down. One is an explicit constraint, which explicitly enumerates the list of legal tuples. So for example, red, green, green, blue, whatever is allowed, you actually write down the assignments that are legal for those variables. And that's a reasonable thing to do, provided there aren't too many variables involved. We also had a notion of an implicit constraint. And an implicit constraint takes a couple variables and their values, executes some simple code, and then tells you whether or not it passes. For example, adding up the values of a bunch of variables and checking whether it's greater than n. That would be implicit. You execute code in order to find out whether an assignment is satisfying. We talked about constraints being either unary, which says this variable can take on these values. That's really just the same as having a smaller domain for that variable. Binary, meaning they involve two variables at the same time. That's different from the variables themselves being Booleans. Okay? Binary means two variables at a time. And n-ary, where a constraint touches multiple variables. Most of the things we've seen have kind of been the binary case, but you can generalize this stuff to the n-ary case. So what are the goals? Well, let's say we have some CSP like the one that's shown here. So here's a CSP for map coloring. There are 3 variables. Each one would correspond to some country, although it couldn't be this map because this map has more countries than 3. The arcs indicate the presence of a constraint between 2 variables, and the fact that there's a little inequality sign there tells us what constraint it is. There are many possible constraints on these 2 variables. These ones happen to have inequality because it's a nice example for slides. Most constraints are not inequality constraints. So what do you do with a CSP like this? Well, the goal we take in this class is to find a solution, right? So the algorithm should chug and then hopefully quickly present you with a solution or tell you that no solution exists. But you can do more things. So for example, you can adapt these same methods to find all the solutions or find the best solution if you have some cost notion, like if certain values in the domain are preferred over others and so on. We're not going to talk much about that till we get to Bayes nets, which will generalize a lot of those things. For now, we're just trying to find a solution. And remember, we had a basic algorithm that we kind of started with and then built it up into kind of a much more augmented, fancy thing. So this was a recursive implementation of a backtracking search. It's basically depth-first search. You might say, how come this depth-first search is recursive, but the one we learned a week ago involved a fringe? Well, they kind of do the same thing. There, the kind of core idea was taking things on and off a fringe. Here, the core idea better fits with a backtracking search, but it doesn't really matter how you do it. All right, so how does it work? Well, you start with an empty assignment. That's here, right? And this is important for these kinds of methods. They start with an empty assignment and build it up incrementally. If you manage to complete your assignment, you're done, you return it. Otherwise, you pick the next variable to work on, and we do that according to some ordering criterion, and we talked about various ordering criteria. Then, once you've picked a variable, you go through the values in order. Okay, what order? Well, there are various ordering criteria for values. We talked about some of those too. In any case, you're going through them in some order. For each option, you check to see whether or not it breaks a constraint. If it does, you stop. Unlike search, where there was just a goal test, here we have a kind of incremental goal test. As soon as we break a constraint, we don't keep going. We extend our assignment, we recurse, and then we kind of return things appropriately and back out. So that's the basic idea, right? You extend things one by one, you check at every point whether you're breaking the constraints, and you do a kind of a good job at deciding what work to do next to the extent that you know. We had some more ideas beyond ordering. So we already talked about the basic ordering ideas, which were that when we're choosing a variable, right, some variables are going to be very unconstrained. They have lots of elements in their domain left. Some are going to be very constrained. And remember, once your domain goes to 0, then there's no solution left. So the smaller your domain, kind of the closer you are to failure in some general sense. You can't actually prove these heuristics are going to work for your problem. But in general, a variable that doesn't have many values in its domain is it's near failure. You want to work on those soon because when they fail, you can backtrack, and you don't want to be backtracking across a whole bunch of other stuff. So for picking a variable, you want to do the hard stuff first. That was minimum remaining values, MRV. And when you're going over values, right, then you want to choose the one that's most likely to work out. And we had this notion of a least constraining value, which says choose the value which eliminates the fewest options on neighboring nodes. Okay, so that was ordering. What order do you pick variables? Do the hard ones first. What order do you pick values? Do the easy ones first. And then we had this notion of filtering, which was about ruling out elements of the domains of variables that don't have assignments yet. Okay, and this was forward checking and arc consistency. We're going to talk a little bit more about arc consistency today because we're going to extend it. But you did some computation that crossed a bunch of stuff off. And of course, the more filtering you do, the more crossing things off you can do, and maybe the less backtracking you do, but you take all this time doing the filtering. And there's no real rule that says how much filtering is the perfect amount, but usually some filtering is beneficial. So we did ordering and filtering last time, and today we're going to talk about structure. So we're going to talk about how to exploit the structure of these problems. And really, kind of, if you take all of this together, this is a bunch of ideas which are general purpose, in the sense they're not about map coloring, they're not about the n-queens problem, they're not about circuit layout. They're kind of about generally what happens when you have variables and constraints and so on in a kind of generic setting. But they really work very well and can give huge gains in speed. They can also not work, right? So there's nothing that says these heuristics are going to work for you. There's nothing that says filtering is going to help. And there's nothing that says there's a way to exploit structure. But in general, these ideas are very effective. All of that said, you can pull out every fancy method we talk about, and you can speed things up and speed things up. But in the end, solving a CSP is an NP-hard problem. It's basically the same as Boolean satisfiability, which means it's basically the same as a whole host of other things, integer programming, things like that. So there are always going to be instances that are hard. The hope is for the kinds of problems that we see in practice, we can make them fast enough that we can use these technologies in the real world. Okay, so let's remember what we talked about with arc consistency. And remember, arc consistency had to do with looking at an arc in the graph, which was an ordered pair of variables, and kind of pulling it over and checking to see whether there was something fishy going on at that arc. So we had this mnemonic that you always delete from the tail. And you can think of this as whenever the arc consistency police pull your arc car over, they check what's in the trunk. Okay, and they remove anything that shouldn't be there. So let's remind ourselves what this does, because what we're going to do today is we're going to extend it. Okay, so let's imagine we get to this situation. And if you'll remember, we had a map coloring problem on Australia. Okay, the Australia map is shown there. And at this point, okay, both on the left and the right, you can see a partial assignment. So you can see from the partial assignment here that Western Australia has been assigned the value red, Queensland has been assigned the value green, and everything else is unassigned. Over here on the left, what you can see is that, again, the solid blocks, just for the purpose of these slides, indicate assignment. And all of these other ones, so like, for example, V here has 3 values left in its domain. It hasn't been assigned, and we haven't filtered anything either. And T only has 1 thing in its domain. So even though we haven't assigned it, we filtered out all but one of the values. So, among other things, if we were following the minimum remaining values heuristic, we should work on NT and SA and not on V. That actually makes sense over here, because NT and SA are kind of in the part of the graph we're working on, and V is kind of off unconnected. So, okay, but setting that heuristic aside, let's take a look at what arc consistency does. So we look at this CSP right now. Right? It's been partially filtered already, and we can look and say, is this CSP consistent? And if not, we can make it consistent by deleting some values from domains. So we look at various arcs. So we look at this arc, if you'll remember this example from last time. And we said, is this arc consistent? So again, we pull over here this arc, and we look to see what's in the trunk, which here is V. And we ask the question, what does consistency mean? Consistency says, is there anything in the tail, in the trunk, that's going to guarantee failure here on this arc? Well, if I choose red at V, then I'm okay because I can choose blue. If I choose blue, I can choose red. And if I choose green, then I can choose either. So it's fine. This arc is consistent. It gets the stamp of consistency. We can go to another arc, like this one. We say, is this arc consistent? So we look at the tail. If I choose blue at the tail, am I guaranteed a disaster? No, right? So this arc is also consistent. If we look at this arc, however, which is the same variables, just in the other direction, I look and I say, all right, if I choose red at NSW, I'm okay. But if I choose blue, I'm in trouble. And so what the notion of, is it consistent? No, it's not. How do we make it consistent? We remove this from its domain. So deleting from the domain of the tail is how we go about making things consistent. And now, of course, we come back here, and maybe the answer's changed, right? So whenever we delete from a variable, right, the reason V was consistent, it had to do with options at NSW. And if options at NSW vanish, we need to recheck this V to NSW arc. And in this case, there's now something I have to delete from V. What has to go? Red has to go, because if I choose red, then I guaranteed a constraint violation. It used to be okay because we used to have blue at NSW. Blue's gone, so now red has to go from V. And in this way, we're propagating information from variable to variable without actually assigning anything. We're still just filtering. All right. Now we look here at this arc, right? And we say, well, neither of these variables is assigned, but based on the filtering we've done, this arc is not consistent right now. Okay, why? Because if you choose blue at SA, there's no legal assignment at NT that avoids a constraint violation. The only way to fix this is to delete from SA, and of course, once you empty a domain, you know that there's no possible assignment left, and you can return failure. Okay, so that idea of going from arc to arc, enforcing consistencies of arcs, possibly rechecking them, that's the foundation of an algorithm that we talked about last time. We're not going to go through it again in detail, called AC3, which is an algorithm for enforcing the arc consistency of an entire CSP. Okay, if I take a CSP, which may or may not be arc consistent, and I use an algorithm like that to enforce arc consistency, I prune a bunch of stuff, right? I'm left now with a kind of sub-CSP, same variables but fewer domains, that is now arc consistent. What does that mean? Well, hopefully it means that we don't have to do as much backtracking. But when you're done enforcing arc consistency, as we saw last time, a bunch of things can be true. You could have just one solution left, or you could have just one solution left, you could have multiple solutions left, you could have no solutions left, and you don't really know from looking at the CSP. So if we remember this example here, this one is arc consistent, right? You can check it yourself again. We did this last time. It's arc consistent, and there are two solutions living in there, right? They're kind of in, superposition. They're both in there, and until you assign some variable, both are still possible. Down here, there are no solutions left, even though it's arc consistent. Okay, and let's be very clear, because this example is going to come back again. The arcs are all the same, right? And each one, if you choose red at the tail, you can choose blue at the head, and vice versa. So all 6 of these arcs are consistent, which means the whole CSP is consistent. We know there's no solutions, and the reason there's no solutions is because if you have kind of all 3 variables at once, you have a problem. But no 2 variables alone are enough to expose it. And that's the deal with arc consistency. It only makes sure all the pairs are kind of okay. It doesn't check triples. Any questions on that before we extend it? Okay, let's talk about the notion of K consistency. Sometimes the thing that pulls you over is even more powerful and is going to check even more than an arc, right? And so this big guy here, I guess he enforces K consistency. So you have this notion of not just arc consistency, but consistency in general. What does consistency mean? We keep saying this word. And actually, we're going to say it in a bunch of different settings in this class, and it's going to mean slightly different but kind of abstractly connected things. Consistency here means does not violate a constraint. So what does it mean to say one consistency? Well, that means nodes of size 1, collections of nodes of size 1 are consistent. What's that mean? That means that each node contains a value which meets that node's unary constraints. That is, you look at that node, and there's some way to escape failure there, right? It's not really interesting, right? You enforce the unary constraints, and if there's any empty domains, then you just stop. So one consistency is kind of too simple to be helpful. But that's what it is, just for kind of mathematical inclusion here. What is two consistency? Well, two consistency, right, here's one consistency, that's a single guy. Two consistency is shown here. Two consistency says it's about pairs of nodes, right? So you pick up two nodes, any two nodes. Okay, a CSP is two consistent if whenever you pick up a pair, if you have a consistent, meaning no constraint violation, assignment to one, it can be extended to the other in some way without violating a constraint. So for every pair of nodes, if you can assign to one, you can assign to the second. Okay, we already know that. That's our consistency. That's exactly what it means to delete everything from the tail in the way we talked about, right? So we know what two consistency is. We've called it our consistency, but there's a more general notion of k consistency that says if a CSP is k consistent, it means if I pick up k nodes at a time, right? In our consistency, I looked at pairs. That's why we called them arcs. I pick up k nodes at a time, and I say, take k minus 1, that's these guys, k minus 1. If I find a way to give them a legal assignment, then if I'm k consistent, any legal assignment to k minus 1 has an extension to the kth node that won't break a constraint. Okay, so what would that mean? For example, 3 consistency says, pick up any 3 nodes. If you can make 2 of them happy, then there's a way to make the third one happy, given the constraints among them. Now, as you might think, right, 1 consistency is trivial. 2 consistency involves an algorithm that we had to spend a kind of fair amount of time thinking about. And 7 consistency, wow, that's going to be bad news, right, to try to enforce that. The higher the k goes, the more expensive it is to enforce these through computation. And the main thing you need to know in this class is the k equals 2 case, which is arc consistency. But they're all there. But let's look at this case here. Remember, down here at the bottom, it was arc consistent. But we can look at this and say, is that thing 3 consistent? So if I take these 3 nodes and I say, consider a consistent assignment to these 2. Like what? Like red-blue or blue-red. Okay, those are the consistent assignments. Is there a way to extend them to the third node? No. So this graph down here was arc consistent, it was 2 consistent, but it wasn't 3 consistent. And if we had bothered to enforce 3 consistency, then we would have detected that. Question?
How would you structure your data say you recently cleaned a combination of 2 assignments?
Oh, great question. Okay, so remember in 2 consistency, how did we make it something 2 consistent? We deleted from the tail. Where? How do you delete? Well, you go into the data structure that holds the domain, right, and you pull things out. So it's easy to delete in 2 consistency, arc consistency, because it's the same as shrinking a domain. How do you delete to enforce k consistency? Say here for path consistency, for 3 consistency here. Well, you would have to say, all right, red-blue is not an okay value for these 2 variables to take. And whenever you say that there are pairs of values on a pair of variables that's okay or not okay, what's that? That's a constraint. So if you want to enforce 3 consistency, you end up with limitations on pairs of variables. Those are actually constraints, which means your algorithm goes along adding constraints everywhere. Okay, one of the many joys of 3 consistency, and one of the reasons we usually use 2 consistency. Yep? So these things do get exponential, and of course you'll see in a slide why they have to. Yep, it's a great question. Okay, so that was k consistency. K consistency is something like 8 consistency. If you can make 7 nodes happy, you can always extend it to an 8th, right? Strong k consistency says consistency of level k and below, right? So it's maybe actually what you thought when you heard consistency. So the claim is this: if you have strong n consistency, right? What's n? N is the number of variables in your graph. If you have strong n consistency, you can solve without backtracking. Why? Well, pick any variable, right? And 1 consistency tells you there's a way to meet its unary constraints. Choose a second variable. Well, there's an arc between them. Arc consistency says whatever you did at variable A, you can extend to variable B, right? And so you do it. Now, 3 consistency says since you've got a pair that are assigned, whichever third variable C you pick, you can extend to, and then you can keep kind of doing this argument. So essentially, I gave you the inductive argument unrolled a little bit. You know, you get the idea. If you have strong n consistency, you eventually can solve. And that means enforcing n consistency has to be just as hard as solving the problem in the first place. And since that's, as far as we know, is exponential, and in particular it's NP hard, it means n consistency has to be NP hard as well. But there's a lot of middle ground between 2 consistency and n consistency. You know, the main other thing people use is 3. This is called path consistency. You think 3 variables form a path. We're not going to do an algorithm here in this class for path consistency, but you should have this idea that our consistency is the first of multiple steps that you could go that would do more and more filtering in exchange for catching more and more kinds of errors early. Any questions on that? Yep. Yeah, so, okay, good question. How come 7 consistency doesn't imply 6 consistency, right? And like I said, the strong notion of consistency is maybe what popped in your head. There's this worry that when you actually write down consistency, that the if part could be vacuous. There could be no consistent assignment to the n-1 variables that to extend. And the strong notion of consistency guarantees that you can get there. Okay. So that was kind of taking one step beyond our consistency, seeing that there are other notions of filtering that could be even more aggressive, right? But even with our consistency, you're not guaranteed it'll be faster, though usually it will be. Now we're going to talk about a completely different kind of approach, which has to do with exploiting the structure of your constraint graph. This is going to work in a pretty different way, and one of the nice things about structure here, aside from the fact that you actually can prove something about the speedups you get, is that these same ideas that we use for structure are going to show up again when we talk about Bayes nets in the middle part of the class. So, what's the idea about structure, right? So, in this law enforcement metaphor, you look at this kind of graph, there's this tangled web of everything, and sometimes there's some like linchpin, something that you can use to break something up into smaller problems. That's not the only kind of thing you can do with structure, but it's a good idea and the kind of thing you want to think about. So, how do we exploit problem structure? Well, there's an extreme case of independent subproblems. So, for example, in Australia here, we've got actually 2 graphs. The one we normally use for examples, the top graph, the mainland, and then Tasmania, which is an island. And for the purposes of map coloring, they're independent problems because there's no constraints between those 2 sets of variables. Now, it's not super interesting because one of the sets only has 1 variable, but you know, we could do Australia separately from, say, North America. That's an extreme case, when subproblems are completely independent. How do you know when problems are completely independent? Well, you can look at your constraint graph, and even without knowing what constraint exists between these variables, right? So from the point of the constraint graph, what's going on between WA and NT? I don't know. There's just some constraint there. Now, we happen to know it's inequality, but you know, from the constraint graph, all you can tell is that there's a constraint. So if you look for connected components of your graph and you find separate connected components, we know they're independent problems, we can solve them separately. And this is super powerful. So for example, let's do some back of the envelope. Let's say you had n variables, and instead of having to solve a whole CSP of size n, right, which as far as we know is of cost d to the n, now we're going to solve a bunch of subproblems of size c. So how long does it take to solve a single subproblem of size c? Well, d to the c, right? It's still exponential in the size of the problem. But now we just got a bunch of small size c problems, so n over c of them. And so now we have this worst case solution cost that instead of being d to the n, exponential, okay, is now linear in n, and it's exponential only in the size of c, the subproblem. So you had this giant problem, which was a mess, and you've broken it into a bunch of, you know, tiny little subproblems. Okay. Here's an example. If n was 80, which is kind of small, right? 80 is not that many variables. D is 2, that's just binary. And you were breaking things up into problems of size 20, which actually isn't that small either. Then you would have 2 to the 80th if you solved the whole thing exhaustively, which means 10 million nodes per second. Back of the envelope gives you 4 billion years. That seems excessive, okay? But you break it up into now 4 problems of size 20, and it only takes 0.4 seconds. I'd rather it run in 0.4 seconds rather than 4 billion years. Probably you would too. Okay, so this sounds great. Now, what's the bad news about independent subproblems? Yeah, there are no independent subproblems, right? This is just not going to happen because you have some problem that's interesting, like how am I going to route all of these trucks to pick up their packages or whatever? And the reason you think of this as a problem is because it kind of is a dependent big chunk. right? You've already kind of separated out the continents or something like that when you formulate these problems. So it's very uncommon to find a problem that's composed of bunches of little problems. So that idea, though powerful, isn't going to be frequently helpful. Okay. Here's something that is a little bit more likely to show up in the kinds of graphs that you're going to see, or if you don't have this, maybe you can arrange for it. So this is when your CSP, rather than being disconnected, which is rare, is tree-structured, which is a much more relaxed criterion. So what does tree-structured mean? It means there's no loops, right? You can set everything up so that there are no cycles. And the theorem says that if your constraint graph has no loops, then the CSP can be solved in time that is linear in the number of variables. Okay, not exponential. That's a big difference. It goes from basically intractable to super efficient when you go from a generic graph to a tree. Okay, so the general case was d to the n. Now it's n times d squared. This is actually going to show up again with Bayes nets. The same idea. If your Bayes net is tree structured, it will also be efficient. And this is a really important example of how restricting your expression language syntactically can change the complexity of the kind of reasoning that you have to support. Right? And this occurs not only in many areas of AI, but other areas of computer science as well. All right, let's see how that works. So here's an algorithm. I'm going to show you the algorithm, and then we're going to talk about why it is fast and why it's correct. And then we're going to talk about what you do when you don't have tree structure, which actually you usually won't. Okay, so here's the algorithm. Assume you have a tree-structured CSP. First, you do ordering. You choose a root variable. So what do we want to have as the root? I don't know, how about A, right? You pick a variable to be the root, and then you order it so that all of the other variables have now directed arcs away from the root. So you think about this like grabbing this CSP by its ankle at A and kind of holding it and letting gravity pull everything else downward, and that gives you an ordering such that you have directed arcs that all go in one direction from the root outward, okay? So here we might, for example, if we start with A, get this tree. We can now have a linear ordering. All of the arcs go from left to right, and there's no cycles. Okay, so that was the ordering step. Each of the nodes is going to have some domain, and to keep this simple, we're still going to have inequality constraints, and I'm starting with slightly smaller domains just to kind of keep the example small. So those domains are now shown here, and you don't want to think that there's necessarily filtering going on or anything to make them small. In this example, they just happen to have these domains. Okay, so what do? I now think that each of these variables, they're arranged left to right. And for each variable, it's got some domain of allowed values. We did ordering. Now we're essentially going to do filtering. Okay, so how's filtering going to work? We're going to go around doing the only thing we know how to do, which is looking at arcs and making them consistent by deleting nodes from their tail. All right, we're going to do the arcs one by one, but there's a very specific order we're going to follow. We're going to go backward from the right to the left. We're going to go variable by variable, and we're going to make the arc that's inbound to that variable consistent. So let's do it. So let's start with the variable f. What inbound arcs does it have? Well, in this graph, it only has one inbound arc, d to f. Could it have another? No, right? You can only have one parent, because this is a tree. This is why it's really nice to have a tree. All right, so we look at this arc. Right now, we're looking at the arc to d to f. We're going to make it consistent, which means deleting from what variable? Delete from d. Okay, so does anything from d need to go? Let me get my white back. Okay, so yeah, we look at d and we say, well, you can't assign blue because then there would be no extension to f. All right, we've made f's parent arc consistent. Now we go to e. D points to e as well. So now we look at d to e and we say, is that consistent? Do I need to delete anything? Nope, we're good. Red extends to whatever and green extends to blue. Now we go to d. D's parent is b. Do I need to delete anything? Looks like no, I'm good at b. Then I look at c. C's parent is b, so I look at the b to c arc, and I see that b can't be green without guaranteeing a violation at c. And then I look at a to b, and a can't be blue. Okay, so I touched each arc once in a very specific order. Now remember, in the AC3 algorithm, we have to go back and check things again. We're not going to do that. So we've done arcs, making arcs consistent in one direction. Okay, we pulled them all over, we did our action, and now we're going to assign in the other direction. Okay, so what does that mean? It means you start at A, and you go the other direction. So at A, I need to pick a value. Well, there's only one left, so in this case, we'll pick it. We go to B, and I pick a value. Well, am I actually guaranteed there's a way to assign it B that won't get me in trouble? We actually are, right, because A to B is consistent, right? All right, now I get to C. Am I guaranteed that the choice I made at B is going to pan out at C? Right? I may have to make a choice at C, but I know that one of them is going to work because B to C is consistent. So I pick something there. Okay, now at D I've got options, right? And so am I guaranteed that they're all going to work? No. But I am guaranteed that something at D will work because the B to D arc is consistent. Which one should I pick? I might worry. What if I pick the wrong one? Right? I might have to backtrack. Don't worry about it. Let's pick green. Okay, so I assigned green at D. Now I go to E. Now I didn't actually, in some sense, pick the best thing at D in terms of keeping my options open, but because D to E is consistent, I'm going to have a choice, which in this case is blue, and then when I get to F, I'll have blue. And so I managed to assign everything, and at each step I was guaranteed an extension because of the consistency of that single arc, and so I managed to do the whole thing without backtracking. Right? So you go one direction doing consistency and the other direction doing assignment. Okay. What was my runtime? Well, it's linear in the number of it's linear in the number of nodes because I go and visit each node first in one direction, then the other direction. And what do I do at each node? The most expensive thing I do is enforce the consistency of that arc, which means enumerating over the paired domains. Okay, so that's ND squared. Super efficient. One pass rightward, one pass leftward. Okay. Can we prove that this is going to work? Okay, claim 1, after the backward pass, right, that's when we go leftward, enforcing the consistency of the parent arcs. The claim is that all the root to leaf arcs are consistent. Well, when I pick an arc up and make it consistent, it's consistent. The worry is that something comes along later and messes up what I did. So for example, maybe I made this arc here from B to D consistent, right? And so it's consistent right now, but then somebody came along and messed up my proof of consistency. Well, how could that be? The only way to make this arc stop being guaranteed consistent is to delete something from D. But that's never going to happen because I'm headed in the other direction as I do this processing. Okay, so you become consistent, and because of the direction you're doing the variables, you remain consistent. All right, so now we know all of the arcs are consistent when that one single pass is done. We couldn't do AC3 in a single pass, but this you can do in a single pass. Claim 2, right? We know they're all consistent. If they're all consistent, then forward assignment won't backtrack. Okay, this is kind of the important part of the proof. So we're going to do this kind of by induction on position. I'm not going to actually roll out the whole induction. I'm going to show you the key point why this is true. So for example, actually, I guess we already did this, right? So for example, you get to some node. For example, it's time to assign it at F. Well, how many parents can F have? 1, because this is a tree, right? What has been assigned at D? I don't know, but something, right? And D to F was consistent. That consistency means that whatever you chose at D, you can extend to F. So we're done. Maybe we just revolutionize the world here without meaning it. Maybe this algorithm will actually work on graphs that have cycles too. Right? When did we actually use the tree, and do we really need it? Can't we just run this on everything? Well, let's think about it. It's time to assign to F. F has one parent, which is D. What would it look like if this weren't a tree? F might have another parent. F might have E as a parent too. Okay? So what? We're guaranteed that whatever we picked at D will extend to F. There's some way to complete that assignment at F. We're also guaranteed that whatever we picked at E will extend to F. So what's the problem? The problem is whatever choice at F makes D happy might not be the same choice that makes E happy. So we're not guaranteed that we can take D and E at the same time and make F happy. And that's exactly what happens when you have arc consistency and not, in this case, we'd need 3 consistency or path consistency. All right, so there's an algorithm. We showed how it works. We showed how fast it was. We showed why it's correct. And it's only going to work on trees. Any questions on this? Yep. That's right. So So there are arrows here. The arrows are here to remind us what direction things are going to work in when we go and we talk about the consistency of a directed arc. The constraints are still undirected things. So thank you for pointing that out. That's right. Any other questions on tree structure? Okay. What's the good news? The good news is trees are a little more common than disconnected things. What's the bad news? You're still never going to see a problem that's going to be a tree unless it's a very special problem. So how come we just spend all this time proving an algorithm that applies to trees when we don't have trees? Okay. And the key idea here is that even if something isn't a tree, maybe you can make it a tree. Okay. So now we're going to talk about improving structure. Remember what I said way at the beginning of the structure when I said sometimes there's like some node that's messing everything up, and if you could remove that node, somehow the graph would break up into pieces or everything would be nice. We're going to cash out on that idea right now, and then we'll do our break. Okay, so the idea here is that even though you may not have a tree, maybe you have something that's nearly tree structured. What does that mean? It means that if you deleted a couple nodes, which of course you can't in general do, right? But if just a couple nodes would just go away, what the structure that would be left would be easy, meaning it might be disconnected or it might be tree structured. Okay, so in this case, for example, in the Australia graph, if you could only delete South Australia, the remaining piece would just be this nice chain that we could solve with the tree-structured algorithm. Okay, so there's this idea of conditioning, which gives you an algorithm called cut-set conditioning, which lets you do exactly this. It lets you, for a price, delete a node from your tree, so in the hopes that what's left over will somehow be efficient because of its structure. So what conditioning means is this. When you condition on a variable, so for example, here we could talk about conditioning on the SA variable, what we do is we instantiate it. That means we pick a value for it. Okay, how do we know what values give rise to legal solutions? We don't, right? But you instantiate it to some value. So you assign SA, right? And you're making a guess as to what it's going to be. But you assign SA, and now what happens? Well, if SA has a fixed value, say green, then there's not really so much a constraint here between these two variables. SA has a single value. Now that value has consequences. So on WA, the choice of green at SA means what? It means we now have a constraint on WA that says WA must be red or blue. But that constraint, it used to be a binary constraint, and now it's unary, because it only involves the remaining variable. So in other words, we instantiate SA. We then take all of the constraints that involve SA, and we project them down to their unary versions, or in general, n-1 versions. And then we're left with a CSP that's kind of the CSP for the case where SA has that value. All right, so here's the algorithm. You instantiate in all ways some set of variables. You then run the tree-structured algorithm on what's left. But of course, you didn't actually know how to instantiate those variables, so you got to do it in all the different ways. So there's part of this algorithm that enumerates possible cut set values and then does something efficient for what's left. So let's see that. You start with your bad graph. You choose a cut set. In this case, SA is going to be our cut set. You instantiate it in all possible ways. Because remember, maybe only one of these works. So you still are going to have this thing where you have to enumerate something, and it's going to be the values of the cut set. But for each value of the cut set, you compute what's called the residual CSP, which is where you project all those constraints down. Okay, and now we have a smaller CSP. They'll all be slightly different. They'll have the same constraint graph, but the specific constraints that are left on the nodes will be different. For each of these residuals, you solve it with a fast algorithm, and then you return. Okay. How is this going to be fast or not? Well, you're going to have a factor from this, which is going to be exponential in the size of your cut set. But this stuff down here is going to be linear in the size of what's left. So if your cut set is small, this can be a big deal. And this means you don't need a tree-structured CSP. You just need a CSP that can get to tree structure with the deletion of a small number of nodes. And then you can use the cut-set conditioning algorithm. Questions on that? Yep. Okay, how do you determine whether a CSP can be made into a tree structure? Okay, you can always do it. You can always delete all the nodes. Right? So the question is more kind of what's the best way to do this? How do you find the smallest number of things to delete? Any way you phrase this, what's the smallest number to delete, what's the best set to delete, it's going to be NP-hard. So the answer is you don't. right? But sometimes you know something about your graph that lets you do this. Sometimes you have some separate procedure which hopefully produces something less than the whole graph and says condition on these. There is no general algorithm that's guaranteed to be any faster than solving the CSP in the first place. But for specific problems, you often know enough about the domain to figure it out. So I realize it's kind of a little unsatisfying. The bottom line is CSPs are NP hard, so really any piece of this that would be really, really kind of make it really fast is probably also NP hard. Yep?
Do you get any benefits by doing this maybe halfway or piecemeal? Like maybe you don't have an efficient algorithm, you run it over to see which node has the most connections to other nodes, and try to chop that code up.
Oh, okay, so the question is, are there reasonable ways to produce a good cut set? Right, like maybe try to take nodes that are highly connected and see what your graph looks like. Yeah, so there are plenty of things, and you could imagine more and more of these things, especially if you know something about your domain and your graph. There's just no algorithm that's guaranteed to produce the optimal thing. Right? Other questions? So this is really powerful because it basically isolates the inefficient part, which is finding kind of the cut set and enumerating it, and then everything that's left is efficient. But it's not the only way to exploit structure. And in particular, I'm going to talk now very quickly about an algorithm which does this in a pretty different way, but which is very close to one of the standard algorithms for Bayes nets. And so I want to make sure you kind of have a good model of not just that you can delete nodes, but also this other approach, which is more about abstracting nodes. And that'll pretty much do it for structure. Okay, so what's tree composition about? The idea is we have a graph that's not a tree, and we want to make a tree. We already know we can just delete nodes and use cut set conditioning. The different idea here says rather than delete nodes, we're going to break this graph up into pieces that we can sort of think about solving separately, but we're going to then glue them back together in a way that kind of reforms the original graph. So we're going to create a graph which is going to be tree structured, and the variables in this graph are going to be pieces of the original CSP. The constraints in this graph are then going to be glue that builds our CSP back together. So let's see a concrete example. So here's Australia again. Remember, each of these constraints is inequality. And so what we want to do is we want to break this up into something smaller, because right now it's not a tree, and even though it is a small example for this, you could imagine if it were bigger, this would be really inefficient. So here's a piece. This is the subgraph on just WA, NT, and SA, right? So it's a subset of the variables and a subset of the constraints. There's no way to solve the original graph without solving this, so it might be helpful if this thing just kind of got solved by itself. Okay, that seems nice. But there's more to the CSP. Like there's this other part that has NT, Q, and SA, right? This is also a piece of the original. And if we kind of keep doing this, we can break it up into pieces. And in this case, they're triples, but they don't have to be. We can break it into a bunch of pieces, which between them have all the variables and all the constraints. That's nice. These are all small. Let's just solve them. Why can't I just solve that? Well, I can, right? It'd be fast, it'd be efficient, they're small. I could come up with a solution to this CSP really easily. But it wouldn't really work. What would be wrong with just solving this? Let's see if someone... Okay. Okay. Yeah, the common variables. What if I solve the first one and NT is red, and I solve the second one and NT is green? Well, like now I don't even know what my solution is. So I need to know when I solve this that the variables they have in common are consistent. They have the same assignments to them. So what do? I look at these pieces and I say each of you, even though you were originally a subgraph, you're a CSP in your own right, each of you is now a mega variable. So I say the first problem, it's mega variable 1. Okay? Well, what values does a mega variable take on? Well, it takes on values of which are the legal solutions to that piece. So for example, the legal values to mega variable 1 are WA red, SA green, and NTB blue, and so on, and kind of we just enumerate them all. Because it's so small, we can just enumerate them all. And then I go to the second one and say, all right, you're a mega variable, and you've got some legal assignments to your little piece of the CSP, and I keep doing that. So now I have a bunch of mega variables. How did this help me? Well, I can put constraints between these mega variables that say legal values for M1 and M2 have to kind of agree on their overlapping variables. So we have a bunch of constraints now that say for any mega variable that shares variables, they have to agree on those variables. Okay, and What does that mean? It means that for the pair M1, M2, the legal tuples are, and then they are kind of all the assignments to the two of them that agree. So you wouldn't want to do this with kind of big M1s and M2s. But here you go. We now have a tree again. And we have the same kind of efficiency trade-off. If the mega variables are really big, then enumerating all of this stuff for each variable gets really slow. But if you can have the mega variables be small, then it's good, because what's left is a tree is tree structured. Okay. So you have to be careful to make sure the thing ends up as a tree, and in particular, like SA has to be a part of all of these things, and there's some fine print to getting this right, and we're not going to get into the fine print now. There's a star on this graph. By the way, stars on these slides mean that you're expected to understand the idea and the motivation for the idea, but not be able to produce the details of the algorithm. Yep. Oh, right. Okay, so how do you know you're not connecting all these things up? So this is part of the fine print. I set these things up so that SA was in everything between them, right? And there's technically something called the running intersection property that makes sure that all the stuff that you need is between those two variables, and that prevents you from needing an extra arc. But yeah, there is fine print here, and it is important to get right if you want this to be correct. Yes?
What happens if you just like solve mega variable or mega one or whatever?
Mm-hmm. Okay, so the question is, what if you try to just plug into M1 and then lock that in? Well, I mean, in some sense, that is what a backtracking search on the abstracted problem would be. You'd solve, you pick a value for the first one. And for these mega variables, picking a value means solving them. Good question. Other questions on this? Okay, so how about this? How about let's take a break, and then we'll talk about iterative improvement, which is a very different way of approaching search problems and CSPs in particular. So let's take a couple-minute break. All right, louder than expected. Let's get started again. So we're going to talk about a new class of algorithms. In the context of CSPs, they're called iterative improvement algorithms, but in fact, once we see how they work with CSPs, we'll be able to apply them to search in general. So the idea in an iterative improvement algorithm is rather than trying to carefully build up a solution that has no constraint violations, you start off with some constraint violations and then you police them. You go around and you kind of break up things that aren't working. So let's be concrete. When you have a local search method, which is the general class of these things, you work with what's called a complete state. Remember, when we started with the empty assignment and we extended it one by one, that wasn't a complete assignment until you got to the end. And the idea was, hopefully, by the time you got to the end, you would build a complete assignment that had no violations. Here, we start with a complete assignment that presumably violates constraints all over the place. So for example, if we have just a two-node map coloring problem, you've got two nodes with an inequality constraint between them. Well, here's a complete assignment. It's also kind of useless because it violates the one constraint you have. Okay, but every variable is assigned. Okay, how do we use this idea for CSPs? To apply a complete state algorithm to CSPs, you take a complete assignment. There are some constraints that are unsatisfied. And so what you do is you have operators that rather than extending the assignment by adding a new variable, they change the assignment. So they reassign a variable to a new value. Now, when we did the kind of natural search version, we had a fringe. That was kind of, so we had a recursive version of DFS. So where did the fringe live? Right? There was no fringe object. Where's the fringe live in a recursive DFS? It lives on your call stack, right? You know, your fringes can be, it can be anywhere, right? They could be on your call stack. They could be in a data structure. Okay. In the first week, they were in a data structure. Now they were in a call stack. In an iterative improvement algorithm, there's no fringe at all. You have one hope. You've got one hypothesis. There's no backup. There's no plan B. You've just got this thing, and you keep hammering on it until you decide to stop. Okay, so there's no fringe. So there's life on the edge. So you take this guy, and you can then change it. For example, in this case, a smart thing would be to pick one of the variables and change it to blue. Okay, so here's a concrete algorithm. Super simple. While not solved, which means while there is a constraint that is violated, pick a variable, okay, and in particular, the specific algorithm we're talking about here is going to randomly select any conflicted variable. Okay, so you pick a variable, and we're going to do that by picking a random conflicted one. Then you're going to pick a new value for it. And here we're going to have what's called the min conflicts heuristic. And that says when you pick a value, you choose one that violates the fewest constraints. Okay, maybe there's ties, and then you can pick at random. In other words, what we're basically doing is hill climbing, right, meaning making local step-by-step improvements to the total number of violated constraints. Okay, so let's see this in a demo for the n queens problem. So let's go here. All right, so here is the 5 queens problem. And this is a particularly terrible assignment, right? This is about as kind of bad as they come. Red means that variable, and this is the formulation where each row has a variable. So red means that variable is conflicted. And right now they're all conflicted. The number 4 is a count of kind of how many conflicts there are on that variable. So for example, we can pick, so what does this algorithm say? It says pick a variable at random amongst the conflicted ones. So don't not pick the most conflicted one or anything like that. Of the conflicted ones, pick one at random. So maybe my random number generator says pick this one. Okay, so what do I reassign it to? Well, now I have to pick a new value. And here the algorithm that we saw on the slide says choose at random amongst the minimum values of conflict. So if I put it here, it won't be involved in any conflict, so I have to do that. All right, so I pick another variable at random amongst the 4 that are conflicted. Okay, so maybe this one. I'm going to go with don't show again. Let's see if that's effective. Okay, all right, so let's undo that. Okay, we picked this variable, and now we're going to choose a value for it that has a minimum number of conflicts. Well, again, let's choose 0. All right, let's pick one at random. I don't know, this one. Okay, 0. Let's pick this one. Okay, instant solution. Okay, it doesn't always work like that. Let's try that again. Okay, let's do the first one. Okay, now they're all tied, so maybe I pick this one. Now, okay, this 4 looks worse than the rest, but that doesn't matter. I just pick a random conflicted one, like maybe the middle, like maybe this one. I put it where it's 0. Okay, now I'll pick this one. Put it where it's 0. I'll pick this one. Maybe I'll put it here. Okay, so something became conflicted, so now maybe I'll go here, and then maybe here, and then here. And so I might have to do this for a while before I find a solution. Okay. You get the idea. So that is a specific iterative improvement algorithm. You could imagine variants that choose the most conflicted thing. This one has some nice properties. And remember, it's choose a conflicted variable at random, and then pick a best value for that variable. All right. Let's actually see that happening in the big demo. Remember this thing? We did backtracking search, we did ordering, we did blah, blah, blah. Let's forget all that and go to iterative improvement. So unlike backtracking search, which starts with an empty grid, as soon as I choose iterative improvement, I'm going to get a complete assignment that doesn't solve the CSP. So there it is. Okay. Is it right? No, it's wrong. It's got blue all over the place. It's a terrible assignment. Okay. The orange indicates a constraint that's violated. And so every time I hit next, that algorithm I just showed you is going to run behind the scenes. It's going to pick one of the variables involved with a conflict, and then it'll choose a value that minimizes the number of conflicts. So let's press next. Something will change. 1. I'm going to do it again. 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9 steps. It looked like a really bad assignment, right? But I guess it wasn't so bad. Okay, that is iterative improvement. Here's the amazing thing. If you start with a random initial state, my n queens wasn't random. It was like the worst thing you could imagine when they're all in the first row. But if you start with a random initial state, you can solve an immense n queens problem in basically constant time. So with high probability, even for n is 10 million, if you start with an initial random 10 million by 10 million board, you can basically solve this thing instantly. That's kind of amazing. I mean, it's not actually clear what you do with the ability to solve a 10 million queens problem, but you can do it really fast now. So before we were like, oh yes, we got to 25 queens. Now we got to 1,000 queens. Okay, now we're at 10 million. So these things are kind of amazing when they work, right? Really big problems. You start with some constraints, and then they just you kind of push the wrinkles out. Okay, and in fact, it's not just n queens. It's it seems to be the case that for randomly generated CSPs, meaning you choose variables and values and constraints all at random according to some approach, so if you take random CSPs that have solutions, except in a narrow range of this kind of critical ratio here, you basically solve them instantly with this min conflicts algorithm. So what's the ratio? The ratio is number of constraints to number of variables. What happens if you have tons of variables but basically no constraints? Well, then this ratio is going to be small, and you're going to be here, right? Why is it easy when there's tons of variables and no constraints? Well, that seems kind of obvious. Do whatever you want. There's no constraints, right? So if there are more variables than constraints, then it should be easy. How about over here? You would think this would be really bad when there's tons of constraints, right? You've got these couple variables and constraints everywhere. You would think this would be bad. Well, okay, you might not have many options. That's kind of the key idea. Anything else? Yeah, it's a little bit like equation solving, right? There's kind of a right answer, and you push that right answer from wherever it starts all the way through, right? Was there another comment? Yeah, so basically the idea is that at least when there's a solution, even though you have all these constraints, essentially you just follow the one thin path that's open to you. So on both of these extremes, it's easy to find the solution. But there's some kind of magical area in the middle, this critical ratio here, where it's kind of just hard enough that the constraints are difficult, but not so constrained that there's only one solution and it's easy to lock it down, right? So it doesn't always work. This is still an NP-hard class of problems, but unless your problem is like just the wrong ratio, then min conflicts is just great. Okay, so you can think there's this map, which is the space of CSPs. There's this one part that's really bad, right? And that's the hard problems. Okay, there is some bad news. What do you think the bad news is? Yeah. Where's your problem? Your problem is right there. That in general, difficult problems from the real world tend to have that kind of right balance that they're still hard. So yeah, it's still hard, but this is often the fastest way to solve. Now there's downsides to this kind of thing. For example, you could just run and run and run. You don't know when to stop. You may never have a solution. But often you get pretty good assignments pretty fast. Okay, so let's summarize where we're at for CSPs and then take some of these pieces out to the context of general search. Yes, question? Oh, what's the approximate value? It depends on lots. So it's a great question. What were the units on that graph? What were the numbers? It depends on like whether things are binary and how you randomly generate them. Like, I wish I could be like it's E, right? But I don't know. No one knows. It depends exactly on the details. There are papers, by the way, that work out the exact ratio for specific assumptions, but it does depend. Yep. So you're saying what happens when you do iterative improvement and there's no solution? Or equivalently, there's a solution, but you're just kind of out of luck. The answer is it just runs and runs and runs and runs. So if you find a satisfying solution, you know you're done. If you don't, stop when you get bored. Yep. Oh, great question. Why do people have contests for satisfiability solvers when really satisfiability, okay, it's a CSP. It's all the same stuff, right? Satisfiability, a bunch of variables, just like a CSP. They have domains, which happen to be true, false. And then what's satisfiability? Well, it's basically a conjunction of disjunctions. And, well, what are constraints? It's a conjunction of the constraints, and the constraints are disjunctions. It's all the same thing, right? So how do people do satisfiability solvers in these contests? Like, they basically do this kind of stuff. That's like the starting high-powered satisfiability solver will be some kind of something like WalkSat that goes along and does iterative improvement, right? In fact, the detailed studies of these critical ratios are usually in the context of satisfiability solvers. But of course, there are other things you can do, and you can be more careful about your heuristics and when you change things, and there are other approaches people use, and so there is more that can be done. But to a first approximation, yeah, if you had an hour to enter a satisfiability contest, you would probably implement that algorithm. You might not win. Okay, so CSPs, they're a special kind of search problem. The states were partial assignments, though we started thinking about them as complete assignments just now. The goal test is broken up by constraints, which is nice because now instead of just having a goal test at the end, you can have the goal test as you go, which lets you stop early. That gave us the basic solution of backtracking search, which had a bunch of speedups. Ordering. Try the things that are going to work, okay, and do the hard work first so that the backtracking is as painless as possible. Filtering. Think ahead and eliminate the consequences of your actions without actually having to do the backtracking. Structure, change the structure of your graph so that you can use efficient specialized algorithms of various kinds. And we had this idea of iterative min conflicts, which might or might not work, but when it works is sometimes really, really fast. Okay. Any questions on CSPs before we very quickly lift this back to the general context of search? Okay, so local search. People often make this analogy about local search or hill climbing, of which min conflicts is a very specific instance. As going up a kind of mountain in the fog. So you're on this mountain, and you can tell what's right at your feet. You know where uphill is, or at least what's uphill right here, and you know that somewhere there's a solution you're trying to go to. And of course, what's the worry? The worry with local search is you don't actually know anything except what's at your feet, and so you're going to kind of head up this hill, and at some point you're going to get to the top of something and think you've won, but you actually haven't because there's something going on elsewhere, but you can't see it locally. That's the issue with local search, is you know how to make progress as a simple algorithm, but you kind of never know what's happening in other areas of the search space. Okay, but you can apply this beyond CSPs. So tree search, remember, has these unexplored alternatives on the fringe, and that's what gave you completeness. The fact that if this idea doesn't work out, we're going to try the other thing, and then the other thing, and then the other thing, until eventually we've tried everything. Hopefully we won't try everything, but because you'll eventually try everything, then you get completeness. Local search, like min conflicts, you've just got some option, you keep improving it until you can't make it any better. No fringe, that means no completeness. You have a new successor function. So instead of the successor function being to kind of move to another state, right? These are often identification problems, so you take something and you change it, right? And that's kind of a subtle thing, but in context, it's usually easy to see what your successor function would be. And in general, these things are faster, right, insofar as they work, and more memory efficient because you don't have to keep this fringe of all these other things that you might do. But they, of course, they tend to be incomplete and suboptimal. So you really quickly get an answer, and you might not get an answer, and the answer you get might be suboptimal. So sometimes that's what you want, and sometimes it's not. The general idea about hill climbing, you start somewhere, and where you start matters. So often people kind of initialize multiple times, have a bunch of random restarts so that you have a bunch of different things climbing a bunch of different parts of the hill. That can sometimes help with these local problems, but each hill climber starts somewhere, and then you repeatedly move to the best neighboring state. If there's no neighbors that are better, then you quit, right? And so, for example, this robot will probably stop here. Okay. What's bad? It's not complete, it's not optimal, but what's good about it is it's really simple and it kind of gets you started. Okay, here's a diagram that has a bunch of the important concepts. This is a diagram from the book. So here, this is what's called the global optimum, or in this case, the global maximum, right? It is also a local maximum. Local refers to the fact that your neighbors are worse than you. Global refers to the fact that nowhere else in this search space is there something as good. You can tell that you're at a local optimum locally by looking at your neighbors. How do you know you're a global optimum? Short answer, you don't, right? If you really wanted to know, you in general would have to enumerate everything. So you want to be at the global maximum. Hill climbing gets you to a local maximum. Okay, and it's particularly annoying when it gets you to a maximum like this, right? Where like you're basically at a bump in the road, but you think you're done. Okay, anyway, we'll come back to that idea in a second. Okay, global versus local optimum. And then there are these flat regions where kind of things are just changing but not getting any better or worse. And it's very hard to tell the difference between a flat local maximum, where you don't want to waste time kind of fiddling around because they're all the same, and a shoulder here, where you have to change some things without making progress in order to start making progress again. So sometimes you're at a current state, and sometimes it's easy to go uphill, but there's all kinds of things that can go wrong. Things can get flat. There can be a little tiny bump that makes you stop, or you can be at a local optimum that is very far from a global optimum. So what do people do? One thing you do is you just start a bunch of these guys. Instead of having, A, you also have B and C, and you have a bunch of random things hill climbing at the same time, right? Of course, it's linear in the number of these things you have, but at least you've now got multiple shots at getting to a good optimum. So there's again a trade-off between how long you search and how many restarts you do. Okay. There's another cool idea here, and this is one that you don't have to know the details on. This idea is something called simulated annealing, which is cool. It's not, I personally think it sounds even cooler than it is, but it's still medium cool. The idea behind simulated annealing is you really, really, really don't want to be hill climbing in a space like this and get stuck there, because you have to take a tiny downward step before you can continue. And so what simulated annealing says is, rather than looking at your neighbors and taking the best one, which is hill climbing, you have a little bit more machinery. So what's the machinery you have? Right? You still have an initial state, and then you kind of take local steps forever. But rather than just taking steps upward, you have this idea of a temperature and a temperature schedule. So this annealing stuff, there's a physics analogy. Okay? So the idea is you look at your schedule. So you look at how long you've been running, and you extract a temperature. And at the beginning, the temperature is really, really hot, and then over time it cools down. What's that mean for search? Well, if you're done, you just stop. Okay, so how does this work? Well, you figure out how warm things are at the moment, and then you look at your local position and you pick a random successor, not the best successor, not downhill, okay, not uphill. You pick a random successor. Then you look at this random successor and you say, is it better or worse than the current value? And that's delta E, the change in energy. Energy here is kind of how high up you are. Okay, so if the thing you picked randomly is better than where you are, you accept it. You move to that position. So it's kind of like hill climbing. However, even if it's worse, you accept it with some probability. So what determines the probability of taking this random successor that was downhill? Two things determine the probability. One is how bad it is. The further downhill it drops you, the less likely you are to take it. Also the temperature. The hotter things are, the more likely you are, you can think about bouncing around physics style. The hotter the temperature is, so the earlier you are in the search, the more likely you are to take a downhill step. As the temperature cools to 0, eventually you stop taking these downhill steps. And at some point then, this basically turns into, at low temperatures, this turns into hill climbing. And so the idea is you kind of bounce around, you bounce out a local optima, and then in the end you just kind of glide into a landing. That's simulated annealing. It's actually got this cool theoretical guarantee that says that if you run it forever, right, you should always be very, very worried about guarantees that start with if you run it forever. Okay, but if you run it forever and you decrease t slowly enough, which is easy to do because remember you're running it forever, so you decrease t slowly enough, then one, you'll actually get to the global optimum. And even more than that, kind of as you bounce around forever, you will spend an amount of time at a state that is somehow related to how good it is, and as the temperature goes to 0, you'll spend basically in the limit all your time at the best state. Okay, so that's great. This is the first time we got guaranteed something local. There was that word forever, which is a little bit weird. And so, although this sounds like it might be magic, it's kind of like everything else. Hard problems are hard. Even simulated annealing isn't going to help you in all cases. And basically the issue is this. If you were in a local optimum next to a global optimum and you were here, right, how do you get out with simulated annealing? You go downhill. You might have to go downhill 30 times before you go uphill 60 times. Well, what does it take to go downhill 30 times, right? You have to pick that downhill step 30 times in a row and then accept it 30 times in a row without accidentally noticing that the other direction is uphill and going back where you started. So this is where these guarantees are. Essentially, you bounce around in here for a while, but eventually you break out and then you bounce around in here. And you're going to spend more time bouncing around in the high hill because it's harder to accidentally escape. But for that exact same reason, it's hard to actually escape any kind of hill of large size. And so people actually do other things to make these kinds of local searches better. Like think about what are called ridge operators that get you between these basins in some other way. Yes? Okay, so the question is, rather than working really, really hard on your one fancy algorithm, maybe you should just do a bunch of dumb things in parallel. And in fact, that's exactly what random restarts in hill climbing do. I could do 100 random restarts in parallel. Each one's just hill climbing and stopping when it hits the top. So that is exactly the idea behind hill climbing. It's a great intuition. And in fact, for example, sometimes there are ways to do millions of these hill climbings in parallel. Sometimes, actually, it's a really nice kind of parallelization. These even kinds of parallelization sometimes you do on something like a GPU. So in these cases, you can do a lot of restarts, and then you can do something simple with each restart. Okay, one last thing. I want to tell you about something called a genetic algorithm. This is where you breed your solutions. Okay, what are genetic algorithms? In a genetic algorithm, you think of your solution as having hypotheses, right? And it's kind of like local search. You can have one hypothesis, but then you don't get very interesting evolution. So you have a bunch of hypotheses. You have this kind of pool of n hypotheses. And then you have some stages that look like local search, but add in some other new stuff. So you have all your hypotheses. You have some notion of fitness amongst them, which is really just in local search how high you are. So that much is just like local search. Then you have this notion of selection, where you take your pool of random restarts and you keep some of them but not others, right? And in particular, some of them might get duplicated. You might have 2 copies. Well, why would you want 2 copies of the same hypothesis? In local search, you wouldn't. Okay, but in a genetic algorithm, what you do is then you pick amongst your hypotheses and you breed them. Okay, so you pick pairs, you do what's called crossover, which is you take part of one solution and part from the other solution to make a new solution. That's called crossover, and then sometimes there's a mutation operator that flips a bit, and that mutation operator is essentially the hill climbing. So hill climbing would have had one or more of these hypotheses. It would have then had a notion of fitness amongst them, and then each hypothesis would have been varied in some small way. That's the local step. Genetic algorithm inserts this idea of mixing and matching hypotheses so you can make Franken hypotheses. Okay? Is this a good idea? Well, sometimes it's a good idea and sometimes it's not a good idea. Genetic algorithms are interesting because they sound really cool because there's this biology thing, and sometimes they work really, really well, but they are the kind of thing that sounds so cool that they're often applied where they shouldn't be, and so they often get actually a bad reputation, and a lot of times people hear genetic algorithms, and because they're so often misapplied, people will kind of have a bad reaction. Sometimes they make sense. So for example, for n-queens, what would it mean to kind of breed 2 n-queen solutions? It means you take like the left half of one chessboard and the right half of the other chessboard. Is that a good idea? Like, I don't know. I mean, sometimes this works and sometimes it doesn't. Okay. This tends to work when pieces of the search space are mostly decoupled, but have some interactions that you don't really understand, but that are weak. Because then you can solve the pieces independently and let the kind of like some mix of the crossover and the mutation help. But again, when it works, it's a good idea, but it is very tempting to use these things where they're not the right tool. Okay. Any questions on any of that? And what we're going to do is we're going to end here, and next time we're going to talk about adversarial search, which is how you select actions when there are agents in the environment that are trying to make you lose.